Hello, everyone. My name is Alfred Cromwell. I am the founder and president of City Tutoring, speaking to you from the city of Lynchburg, Virginia. And I was thinking of doing this short video. As I said a couple of days ago, I'm going to be doing videos this week on vectors. So I thank my subscriber who described to me what he needed with vectors. But I'm making this specific video as a short video because it's a continuation of the video and I'm posting the link below in the description, the video that I posted last week, which actually almost went viral on the errors that students make when they are dealing with fractional exponents. And I was thinking today, actually, it's actually late in the evening now. And I had a lesson today with a student, very bright student, by the way, but he claimed that my lesson was fried his brain, that he was mentally tortured. Not in a bad way. He said it as a compliment. Um, but again, because we are in the business, and I say we here at City Tutoring, and specifically I as a person, I have a passion for identifying flawed thinking early in life so that we can start to ground you with a solid mathematical foundation. And as the student was telling me that this evening, he was almost on the verge of tears in a good way. And he said, I've never been taught this before. We were talking about the complex conjugate, by the way. For those of you who are mathematical, you know what the complex conjugate is. He said his teacher, and I kid you not, I quote, "My teacher went over complex numbers and she never covered the complex conjugate." And yes, I believe him because he actually showed me the recording of all the classes that were in his school. I was shocked. I'm rarely shocked these days with the problems that we have in America and around the world, but this truly shocked me. And then I started to think about the flawed ways of thinking. In the back of every flawed thought or character trait, even in things that are not related to math, there's a process, if you will, of wicked thinking. Beware the beginning of evil because it starts in the mind. And you start making preparation, you start excusing yourself for thinking this way, you start comparing yourself to others. And then you say, it's not so bad, I'm just going to do as they have done. And you start convincing yourself that wrong is right. Back of every flaw and fall in human character, there's a process of wicked thinking. What process are you engaged now in your thinking? What predicates are you laying for failure? To love your own errors more than you love the truth of math. All right, everyone. So let's begin the lesson today discussing radication. And we're going to be talking about the fundamental properties, which are often not clarified in your classes. And that's why you are on this channel, because you know that here you're going to get the real clarification of and the real definitions as to how to operate with the different the mathematical principles, in this case, powers or exponents. So in general, when we raise something to an exponent, you can typically, I'm just going to use, just to show you the factors here, right? A times A times A times A for infinite. And this, we could call this the M factors. So typically this would be, we have 4 factors here. And this means that you can rewrite this, as you all know, at this point, a to the 4th exponent. All right. So that's for the exponent. Now, when you're dealing with roots, you have a situation that typically you have to learn to label the parts, right? And I see a lot of students, and they often do not do that. So the number that is outside some people call it the radical symbol, other people call it the surd. If you're British, in Britain it's called the surd. So if you have a number like this, and it's going to be inside is the root. All right, this is your index, the root that you want to take. And this is called your radicand. I know that a lot of students don't like to get into the habit of labeling things, but believe me, it makes all the difference when you know what you're dealing with. And of course, the number that you get from this, the answer that you get, if this mth root of n is going to be equal to a, the a is actually, the answer that you get is actually the root. Very important, right? So the index indicates the root that you want. And if you rewrite this, you get a to the m equals n. Okay? So in radical form, it is a mathematical operation where you have two numbers, let's say, and you have an index and a radicand, and you need to be able to find the root, right? So most of you have been working with roots, and by this, if you're watching this video, you have had some exposure at least to finding roots. So what if I asked you, for example, for the cubed root of 64, right? The cubed root of 64. Well, the index here is 3. That means you have to find a number that when you multiply, that when you exponentiate it rather, to the third, you're going to get 64. And the only thing that works here is 4. Why? Because, always ask why. Because 4 to the third, which is the inverse operation, gives you the root that you want to find, right? 64 in this case. All right. What if you want to find the square root of 25? Well, the square root of 25 is 5. Why? Because 5 to the second, right? Normally we don't write, by the way, you notice how in the first one I wrote a 3. In the second one, I did not write an index because when you're looking for, when you're taking the square root, we normally do not write a 2. It is understood to be a 2 outside the radical symbol. And this is because 5 to the square is 25. All right. What if I asked you for the 11th root of, take the 11th of 2048? Well, the answer here would be 2. Why? Because 2 to the 11th is going to give you 2048. So typically, we're going to be dealing with one of the main objectives of this video, though, is see how we can extend these principles to when you have fractional exponents. When you have fractional exponents, because oftentimes they don't clarify certain things. So if you have a fractional exponent of the form a to the m over n, right? Any number raised to the m over n, you can rewrite that as you take the denominator of your fraction, which in this case is n, and you write it as n radical a to the m. Right? Which means you can also take the m outside the radical and put it outside. So this becomes n radical a, and I could just write my m outside like that. Right? I can exponentiate it that way. And if, please write this down somewhere. I'm going to write it down here also, but have it. A lot of books, they're not clarifying these things. If and only if n, in other words, the denominator of your fractional exponent has to be greater than or equal to 2. And if it's not greater than or equal to 2, then this is not possible. So the denominator of your exponent becomes the index of your roots. Isn't that amazing? It becomes the index of your root. So for example, if I gave you 7 to the 1/2, that means the square root of 7. If I gave you b to the 2, let's say variable b to the 2/3, then that means the cubed root of b squared. All right. What if I gave you b to the 1/n? Then that means the nth root of b. All right. What if I gave you an index of n times k? Or, well, actually, let's just do, let's first work with a simpler one, like n to the n radical b to the n. Well, in this case, right, n over n, it would be really n divided by n, which is just 1. So then you would have b to the 1, which is just b. All right. So this becomes n over n. All right. Let's do another one. These are all the fundamental properties that are often they're often glossed over. All right, so have a look at this and copy and see what we can continue. All right, the next one. What if I gave you an index of n times k? So you have nk radical b to the mk. And you wanted to rewrite this. Well, this just becomes your index here is nk, but k over k cancels. So now you have n radical b to the m. Okay. What if I gave you 11 to the 3/4? Well, the denominator here is 4. So that means I could write an index of 4. So this becomes 4 radical 11 to the 3rd. All right, etc., etc. I want to do another one, though, just in case. What if I gave you the nth root of b to the m inside? Well, that could be rewritten as also with the m outside. So you have n radical b to the m. And you're going to see how important this property is. What if I gave you the 12th root of 2 to the 18th? Well, again, your denominator is 12 if you rewrite it as a fractional. So this becomes 18 over 12, right? Which actually simplifies to 2 to the 3rd. Of course, under the radical symbol. And why is that? Well, look at what we've been doing so far. If this is 2 to the 18 over 12, if we reduce this fraction, right, what do we get from here? What is the common factor that goes evenly? Well, we could use 6. 6 goes into 18 3 times. 6 goes into 12, right? And so 3/2. And so there's an index here of 2, so 2 to the 3/2, which is the same as the square root of 2 to the 3rd. Right? You see, you have to be very rigorous with these things. All right, now, when you have fractional exponents, you still are applying the rules that you learned from exponents, except that this time you need to verify them. You can apply them to, just as you do with whole numbers, you can apply them to fractional. exponents. So like if you had 3 to the 1/3 times 3 to the quarter, when your bases are the same, we have said before, when your bases are the same and you multiply exponential expressions, you add the exponents and keep the base the same. So this becomes 3 to the 1/3 plus 1/4. And now you have 3 to the, well, the common denominator here is 12. 3 times 4. And then we have 1 times 4, 1 times 3. That's going to give you 7. So 3 to the 7 over 12. And if you want to rewrite it as a radical expression, it becomes the 12th root of 3 to the 7th. Let me know in the comments down below if you've seen things like this, if they've clarified things like this. All right. What if you have a negative exponent? Let's say you had 2 raised to the negative 1/2. Well, as we've said before, you know, from the laws of exponents, you can always make an exponent positive if you put a 1 over it. So this can be written as 1 over 2 to the 1/2. And if that's the case, then the 2 to the 1/2, if you want to write it as a radical, you can write it as 1 over the square root of 2. Now, what if you have, and this is where we're talking about my previous video on this topic, what if you had a negative base? Let's say you had -9 raised to the negative 1/2. All right. So if you were to apply the laws of exponents, you want to make that exponent positive. So you would have 1 over -9 to the 1/2. Which can be rewritten as 1 over the square root of -9. And this is illegal. Remember we said in the previous video, do not do this. In this case, no real solution. No, but I can do, no. No. There is no real solution here. There is no such thing as a negative square root. I challenge you to find one. What 2 numbers that when you multiply them are going to give you -9? What that are the same? You can't. And that's why you have the complex numbers. So if I see students doing this, I know you have not been taught this by your teachers. I know that you have not gone over this in school. And it bothers me. And it should bother you above all, because you're going to be the victim of this, not me. All right, what if I gave you a positive base, 25 to the negative 1/2? Can I do that? 25 to the negative 1/2. Well, I can make this a positive exponent. I could write this as 1 over 25 to the 1/2. Which I can write this as 1 over the square root of 25. No problem. And the square root of 25 is 5. So this is definitely legit. This does exist. You see the difference? Always comes with the terms of service. All right. So what would be a good way to summarize rigorously these rules? Very simple. If you have, and I'm going to actually write it out. If you have an odd index, but a positive radicand, then you get a positive root, positive power, right? So, for example, odd, and inside you have a positive a, whatever it is. Well, your answer is going to be a positive r, positive root. If your index is even, and your radicand is positive, you also get a positive. If you have an odd index and your root, your radicand is negative, you get a negative r. And of course, if this is where it gets really important, almost exciting in a way, if your index is even, so even index, but a negative radicand, then it does not exist in the set of real numbers. Sorry, I challenge you to prove otherwise. Does not exist in the real numbers, D and E, right? So what are some examples of that? Well, I mean, there are many. You cannot take, for example, the square root of -9. I'm sorry, you can't. You cannot. Right? So I'm going to put them in red and put a big X's over them, right? This is illegal. And stop doing it. Right? This is also, what about the fourth root of -3? Well, you still have an even index and a negative radicand. This is illegal. Stop. What else? What if I gave you the eighth root of -3,000? Even index, negative radicand, illegal. Don't even try it. So in general, let's create a rule. Let's create a fundamental rule. If you multiply any of your indices, right, by 2, you could say that any number twice n, when you have a base of a negative base, does not exist in the real numbers. It's so important to know the sets that we're working with. All right? So we've done a lot of the work already, but I do want to do a problem now. Let's see if you can apply some of the logic behind this then. What if you were sitting on a test and you had the following question? This was an admissions question I gave 2 years ago for students who wanted to take algebra 2, because this topic is actually algebra 1. So we assume knowledge of algebra 1 before you get into intermediate algebra. So if let's say you were multiplying 2 to the 13 over 7 times the 7th root of 2 to the 8th. All right. So how are we going to solve this problem? Well, remember that any number raised to a fraction can be rewritten in radical form, or vice versa. So 2 to the 13 over 7 can be written as the 7th root of 2 to the 13th. Now we're multiplying that by the 7th root of 2 to the 8th. And we now have a product of exponents here. And what happens after that? Well, we already have, in the first that we rewrote it, 7th root of 2 to the 8th, right? 7th root of 2 to the 8th. Make sure you understand why I did that and that you're following along. Right? Now we have 7 radical 2 to the 13th. Notice that this base, I'm going to use, let's see what color I can use. I'll try blue. Why not? Do you all notice the bases here? The radical 2 to the 13th times these are the same bases. These are the same bases. So if the bases are the same, that means we can actually add their exponents. So this becomes 7 radical 2 to the 13th times 7 radical 2. I'm looking at these exponents right here because this can be written outside to the 8th. Isn't that marvelous? So now you just add them. 13 plus 8 gives you 21. So your new expression is the cubed root. Let me just clarify here. I hope you can see it because the blue is not as clear as the other colors. You have 7 radical 2 to the 21. And now you can write this as 2 to the 21 over 3. Right? Because in reality, the reason we're using 3 is because it's the cubed root, right? So if you do it to the 21, we have 21 over 3, which gives you 2 to the 7th. And 2 to the 7th is going to give you 128. All right? 128. So was this video helpful? Let me know. Let me know also in the comments down below if all these things are clarified to you in school, everything we've been doing so far. This is going to be part 1 because I still want to give you more and more exercises on this and more restrictions. All right. Thank you for watching, everyone. And if you liked it, please hit the like button, as they say, and subscribe to the channel because, as I said, we're always growing. Thank you.